The stream is live.
Hello, the stream is on. It normally should be giving a countdown, but no problem at all. And today, this particular session, we're having Kirk Pepperdine, the authority in performance, JVM. I am just so honored to be here with Kirk and also his member of his team, Saint Wasonga, presenting automatic heap sizing for the serial collector. So, the stage is all yours. And also, just a quick introduction. I mean, we all know who Kirk is, but Saint is a member, software engineer on Kirk's team at Microsoft. So, yeah, the stage is all yours.
Backwards. Oh yes, yes.
All right, good.
Stage is all ours. Okay, so oh, and Mary disappeared. Awesome. And look who's here. Hello, everybody. How y'all guys doing? Let's see where we're all from. Anyway, so I see Heinz is in the mix here. So, hey Heinz, welcome to your little island, and Vincent's in here also. No sound either. We actually have sound, right? And Simon, lovely. And we did not see you. Really? Huh. Okay. Mary, I don't know if you can go into the YouTube channel and see what they're seeing, but let's make sure that we have everybody along with us here. All good. Oh no, Vincent's all good. Okay, fancy. Howdy, Billy. Where you guys all from? Where you calling in from? And well, I'd say thank you. Welcome to our session. It's on automated heap sizing for the serial collector, and yeah, everyone might be going like serial collector. That's a thing. Yes, it's a thing. Hello from Ottawa. Oh, Sebastian. Okay. I may be there in a couple of weeks. It'd be kind of maybe we can have a meetup or something. It'd be kind of fun. Okay, this is complaining and Victor. Okay. Well, so let's get into it. So I think through the presentation we'll get to answering the questions like, who cares about the serial collector, and maybe none of you do, and maybe some of you should, but we'll talk about that. So one of the things that that we got into a while back was how should we say it? Just noticing how people were deploying applications, especially in containers and Kubernetes. And of course, there's been this whole discussion about how Java is not container friendly, and we need to make it more container friendly and things like that, or be able to manage what we call like homogeneous deployments at large scale more easily on server farms and things like that. So if you get into microservices, of course, you're going to get replicates of services, and they tend to all be deployed in the same area. And it always creates these interesting problems for the for the DevOps people, because they're looking at, okay, how do I size things? How many can I put on? And more importantly, it's like, do we have some route where we can actually probably like zero out lots of memory use, usually if we have like idle JVMs, because there's a lot of times that we've deployed, things aren't being killed, and we just have JVMs lying around being idle. So it'd be nice. I think this first came up. Who was it? Jelastic was looking at how do we modify the garbage collector to basically fold up and go away, or Java Heap fold up and go away when things become idle. I mean, the real problem with that is like idle is not an event, so it's nothing you can actually trigger from. And yeah, so there's a whole bunch of different problems with the, heap sizing, and everybody's been saying since like forever that we're going to make this automatic, and it's never really worked, right? It always involves tuning, and tuning is a pain in the neck, right? So we got into this idea we're going to like get into automated heap sizing, and when we started looking at it, for reasons that'll become apparent, we said, okay, let's check out the serial collector. One of the ideas is that the serial collector, the code in it is relatively simple, and so it's a good collector for us to start experimentation in, from our point of view. Okay, so automated heap sizing, what is it? How's it going to help? How does it work? And so we'll try to answer these questions. And Saint is here. He's been hacking away in the C++ code. I've been slowing him down wherever I can. So we've been slowly working at this. So let's start with a review of automated memory management. Serial automated memory management with the garbage collector. And really what I want to do is this with a view of all the little bits that we want to touch on, because really what I want to do here is set the stage for what do we need to do in each of these areas in order to support an automatic memory management scenario here. And I'd like to start specifically with ergonomics, and in particular, we'll probably start with startup ergonomics. So first, just my definition of ergonomics, because, why not? Ergonomics are really choices made by the JVM to how it's going to configure itself based on its awareness of what resources are available, and also what are the conditions in the runtime that it's aware of, right? So we need to build in awareness of these things into the JVM. So I've broken this down previously into two different categories of things. Like there's startup choices. So these are configurations shaped by the hardware, choice of the garbage collector. There's also how do we size Java Heap, and we have a generational space, so therefore we have to partition it into each of the different supporting memory pools, right? And with runtime ergonomics, we're basically trying to say, okay, how can we reconfigure or change our choices based on what's happening in the runtime? So we're going to take different performance metrics of the runtime, and we're going to use that to say, okay, how do we resize Java Heap, right? And that's could be based on GC overhead, GC intervals, frequency, allocation rates, amount of free heap before, after. So there's a bunch of different things that we can actually use. In this case, I've said the blue bits are things that are a consequence of the configuration, and the allocation rates are something that we can use, but that's a consequence of how the application is behaving. But of course, there's some harmonics here that we have to deal with. So allocation rate is affected by overhead and intervals, and of course the intervals and overhead are affected by the allocation rate. So there's these tremendous number of feedback loops that you actually have to deal with when you're trying to tune. We'll talk about that, right? So let's take a look at startup ergonomics to begin with. And of course, we're going to do this in the context of garbage collectors. So just to remind everyone, I did a little bit of a timeline, as to the significant releases for garbage collectors. So the dark red dots are when we had to change in defaults, and the light red dots are when we had some major event. Now, in between, people have been working on the collectors to improve the performance and adjust them and make them run better. And so there's constantly work going on inside that space. It's just like these are just the major release points, going back to 1.0, mind you. Right. Okay, so let's take a look at, again, ergonomics, and in particular, how do we select a garbage collector? So here's the, can we say ugly C++ code? And I say ugly because, look at the macros, man. And they say Java's ugly and bloated, but anyways, that's another story, I guess, right? I guess it's not too bad, but anyways, so how do we get here? Or how do we read this, I guess, is another word. So we have OS is server class machine. So we have two different class machines. We have a client class machine, server class machine. This is based on specs in, I'd say, early to mid 90s. So yeah, they might not make sense for the type of hardware we have today, but that's what we're living with, right? So we first need to figure out, okay, what's a server class machine? So here's the method that's going to tell me that. And first we got these two weird flags. I guess they're mostly used for testing, but you can use them yourself if you want. So that will give you all three states. And then, of course, the one we want is the third state, which is go figure it out, right? And so we're going to set that up by basically saying, well, we're going to set the CPU counts to 2, and we're going to set the server memory to 2 gigabytes. And there's a little bit of a fudge factor that we need to take away because sometimes, well, again, we're looking at old address spaces where they had like 2 gig maximum. And so sometimes memory would go missing from that 2 gigs because of different things that got installed, or the operating system would take away memory for one reason or another. So I have this fudge factor that gets taken away from the 2 gigs. So we're gonna run through this bit of logic here, and it's going to get the active processor count, the amount of physical memory, and it's going to do a little bit of a comparison. Now, the active processor count is actually container aware, right? Because after that, we go through a little bit more logic that looks at the number of logical processors. So if you're on bare metal, then that will be are you hyper-threaded or not? And then, of course, you'll get some multiplication and end up with a core count at the end of it. But the net effect of this code is we're going to answer the question is, do we have 2 or more cores, or do we have more than 1792K of memory? And if we do, then we are actually going to be a server class machine. If we have less than that in memory or in cores, then we're going to default to using the serial collector. So you can imagine, what we're talking about are small deployments. And surprisingly, I guess the numbers we have is about 40% of the deployments are small. So you get Kubernetes, some strange configurations, like they'll give you 1,000 millicores and 1 CPU for Java process, which is insane, but that's a very common configuration, not recommended, but it is what it is. So you end up with quite a significant number of deployments that are actually using the serial collector, surprisingly so. And again, it's not a bad choice. Oh yeah, the really weird thing is, like, when I was talking to the CLR engineers, they were saying the idea of fractional cores was really odd to them, because when they first started writing the CLR, and of course the same thing with the JVM, you didn't have fractional cores, you had integer cores. So if you go back into the code, you can see that we have an integer amount of cores. So it probably gives you some idea as to why you end up with milli-cores, because you're going to break a lot of code if you all of a sudden have to use a floating point number to describe a fractional number of cores that you want to use. Okay, cool. Anyways, right. So we are actually using the serial collector here from the Startup Ergonomics. What do we want to talk about next? Oh, this is an aside, and I think that this is kind of important because we've seen people get confused by this when they start talking about containers and sizing containers and how much memory does the JVM use and things like that. We'll get a little bit deeper into that later on. But just a reminder to everybody is that virtual memory is not real memory. You're never going to run out of virtual memory address space, right? Never, right? You will run out of real memory, but you won't run out of virtual memory. And so when operating systems start processes, they like to have contiguous memory address ranges. So they'll set that up in a virtual memory address. But then we have to map that virtual memory address space onto real memory, and then we have to back it, right? So there's really 2 states to consider when you're talking about virtual memory and real memory. is that we're going to reserve memory, and that's going to be reserving like in a virtual memory address space. And then when we go to commit memory, what we're going to do is we're going to take that virtual memory and we're going to say, that's actually going to map onto this chunk of real memory, right? So if you have a lot of virtual memory out there and you start committing a lot of it, you will run out of memory, and you'll get the out of memory killer process coming along and zapping you, right? But just because you say that, like you'll see in when we talk about Java Heap, you'll see that just because we have memory reserved doesn't mean we're running out of real memory. It's only going to be a problem when we actually start committing that real memory. So just because the process 1 gigabyte of virtual memory address space doesn't mean that process is consuming 1 big gigabyte of real memory. It gets a lot more complicated than that, and we'll look at a process and you can see what's going on with this. Okay. Okay, so if we go down to the next bit, what we're talking about is like, okay, so let's talk about heap sizing ergonomics. So we have the serial collector. Now what does the heap look like? And what are the ergonomic choices here? So with heap sizing ergonomics, the first thing we're going to see is like we need, one contiguous space in virtual memory. One, that's a Java heap. It's allocated as, it's reserved as one contiguous virtual memory address space. And the size of this is going to be our standard default 1/4 of RAM, or 1/4 of the memory that's been allotted to us by the C group that we're running in, aka container. I'll probably use the word container now instead of C group, but it's effectively that. Okay. So again, this is reserved memory, but it's not memory that we're actually using because it hasn't been committed. Okay, but it does reserve us a contiguous address space. The next thing we need to do is we need to partition it into generations. And so we're going to have another ergonomic thing here. It's like max new size. And that's going to define the max size of the young generational space. Now, if we're showing you code, you can actually see that the serial collector will reserve, will create a reserve space, and then it will reserve some of that reserve space for young and some of that reserve space for old generation. If you go trolling through the code, that's probably what you'll see. This may also be calculated by a heap ratio. And then we start getting into actually committing memory and starting to back this this memory. Now, how the virtual memory is committed, it works differently on OS X or Windows or Linux. If you're using Linux, what you're going to find is that you actually don't commit the memory until you touch it, right? As soon as I put a value in there, then that's when that memory will be committed, and that'll happen at a page at a time, depending upon your page size. Okay, but anyways, you can see there's a lot more numbers in here. So okay, so we have young gen. How are we going to divide that up? Well, we have an Eden space. How big is that? Well, that's going to be the it's going to be dependent upon the survivor ratio, right? And the survivor ratio, you can look that up and see how it actually works, but it effectively ratios out how much space I need for survivor spaces and how much I'm going to have left behind for Eden. And of course, this is based off an initial heap size, which means I'm not likely to use all of my reserve memory in this particular case, right? And then we get to tenured. And again, tenured is just basically what's left over for the initial heap size. So all of the colored bits, not the gray bits, count against heap size, sort of. Like I said, they really don't truly count until you're touched. But until then, it doesn't count in terms of real memory until it's touched. But you can consider like that's my initial heap size. So that's, for all intents and purposes, how much memory I'm going to use up front. Okay, and then there's some other data structures that we're going to add here. So we need a card table to help us track pointers for scan for roots. We need a free list to help us manage tenured space when it starts to look like Swiss cheese right after a collection. Okay. Let's see how we do for time. Good. Want to leave some time here. So when we get into automatic memory management, right? So like, how do we manage the space? Let's just have a little conversation about that. Now, so when you think about all of these, like I said, about the heap sizing stuff like that, as you can imagine, whatever it is we're doing by hand here, we're going to try to want to automate all of that. So this is why we're going through the probably painful redundancy for a lot of you on how this works, just to remind us, level set us, so that when we actually go to how we're going to automate it, that makes more sense. Okay. So we're going to use the GC mark and sweep tracing collector. Just a few notes here. Java applications are naturally multi-threaded, which is why giving a Java process 1,000 millicores is kind of insane. Even giving it 2,000 millicores is probably still starving it for a lot of, just by how those 2,000 millicores can actually be consumed. Anyway, so Java application is naturally multi-threaded. So you can have one-to-many application threads. We call them mutator threads from a garbage collector point of view. So I might use mutator application interchangeably here. Please don't be disturbed. We have many what are called Java threads. They are effectively kernel threads. So they're the kids threads that have permission to do maintenance and things in the JVM. One of the maintenance things that gets done is going to be garbage collection, right? And generally you can have one-to-many GC threads, but we have the serial collector, so that means we get one thread and one thread only, right? And when we learn how to use that, I guess we can get a second thread, maybe. Okay. Anyways, and Java Heap, of course, is a shared data structure. And so with like any other data structure, we need to make sure that multiple threads accessing it don't corrupt it, right? So in terms of garbage collection, there's a couple of different mechanisms we're going to use. One of them is going to be a GC barrier code, which is going to have the code that coordinates how everybody's going to access the heap. Generally, these things get a little bloated when you talk about concurrent collectors, because that's when it gets a little complicated. But for the serial collector, this is really kind of, and the parallel collector is very simple, because the only thing we're going to use here is exclusive access, right? Mutually exclusive access. In other words, we're going to have this thing called a safe point. And what happens is that if we're going to call for garbage collection, we're going to trip the safe point. And it's going to capture all of our mutator threads, and it's going to capture them at some point where it's safe for them to stop. They can stop without being corrupted by the maintenance work that we're going to do. And in this case, the maintenance work is to basically rearrange and recover memory, right? Now, the GC barrier code is extra code your thread is executing, so therefore that's a overall runtime latency, right? Which is very minimal for the serial and parallel collectors. There's no runtime latency really being added because of this coordination. But safe pointing is a tail latency event, right? So if you get like 100 millisecond GC pause, you can take every incoming request and every request that's in flight and basically say, I'm going to add somewhere up to 100 milliseconds of latency to that particular request, which you may or may not care about. Yeah, okay. Sorry, just looking at the comments here just to see if there's any questions happening. There is something over here. Sorry, let me check here. Okay, fantastic. Okay, so let's continue on here. Yeah, if you have any questions or comments or experience, do please put them out there. Yeah, okay. Yeah, it's actually, there are some quite interesting questions like you can ask, and we'll put them in here. It's like, how many people are actually, shall we say, consciously using the serial collector? Do you know which collectors you're actually using? I guess is another question, right? It'd be interesting to know if you want to put that out there. Okay. Serial collector, typical GC cycle, mutator suffers an allocation failure. That sends a signal out to the system that we need to run the garbage collector. We're going to arm the save point, and when the mutators reach the save point, GC thread runs. It cleans memory, recovers memory, and then when it's done, it will release the mutators so that they can go off and work again. And of course, that time between safe points is going to be our pause time. So so let's look at serial overhead right here. So as we go along, we'll try to start introducing cost models so that you can see some of the reasoning behind some of the decisions that we're making. Okay, so in this case, we're looking at latency overhead. So there's a timed save point. So the threads are not at the save point, they're executing code. They need to get to a save point in their execution where they can stop, right? So that's our time to save point. And then there's time at the save point, which is our GC pause time. Now, this helps us define some metrics that we're going to look at. GC overhead is the total GC pause time divided by the total runtime. And in this case, we tend to aim for less than 5% GC overhead. And the closer we can get to 1%, the better it is. And we'd like to see that when the application is somewhat busy or very busy, or relatively busy, I guess. Getting 1% if the application is idle is probably pretty bad. This could be like high overhead to have GC overhead of 1% when your application is effectively idle, but it's another story. Okay, now let's get into mark and sweep. And this is going to get important because mostly because I think most of you are aware of the steps here, and you can pretty much read them here. But the question is, where does the data get left behind? Because that can actually complicate things later on for us. So trigger young gen collection trigger on allocation, failure in Eden. So we're going to clean the young generational spaces so they all get dropped into a bucket. And then we need to do a scan for roots, which means we need to look at everything outside of Eden and say, what's pointing into here. That'll be our root set. So it means we need to scan tenured, which is where the card table comes into play. That's helpful in reducing the amount of work needed to scan tenured. Right, sweep. Right, so once we get the root set, we can start tracing pointers, mark all of the reachable objects as live, and then we're going to copy all of the objects into some other memory pool. Likely we're going to put it into the 2 pool. The survivor space now that's been activated is the 2 space. And anything hitting a tenuring threshold, in other words, the older stuff, is going to be pushed off into tenured space, right? So more importantly, at the end of the collection, the red bits are where the data is. So Eden is empty. Our 2 spaces should be about 50% full. And of course, we're going to have data in tenured space. Vincent, that's a good question. Who is responsible for tuning the garbage collector, ops, DevOps? Generally, it's a combination of all 3 in my experience. And that's an awesome question, Vincent. Generally the ops are good at deploying things. They don't really generally know anything about the JVM. So when it comes to tuning, they're just if you can't script it, they're scratching their head and running around trying to figure out who can help them. DevOps tend to be a little bit more knowledgeable, but generally they don't have as much of they don't have as detailed information as they probably need in order to do a good job tuning. And I think a lot of the choices that you see, especially with a lot of the bad literature out there that people read, and try using ChatGPT to get good information out of this. It's tricky. But what happens is that you end up with what do we call lost opportunity costs. So for example, I did a tuning with a group that had tuned some applications, and we managed to beat out an extra $1.7 million a year savings by capturing some of their lost opportunity costs. Just because they had tuned reasonably well. Actually, they didn't do a bad job in tuning. They just left quite a bit on the table because of just some of the choices they did make. But anyways, so it can make a huge difference in terms of tail latency. It can make a huge difference in terms of your P50s, and it can make a huge difference in terms of your pocketbook. So so these things are significant. Okay. Right. So if we go to the full collection, triggered by allocation and tenured, and we're going to clean everything. And so all spaces are going to the same bucket. So we'll do the same scan for roots. We just don't have to go through tenured like we did before because everything's in the bucket. Mark, trace, reference all live objects. So it's the same dance, right? Except for it's just like with the entire heap instead. Now, the problem here is that the tenured space is known as an in-place collection, whereas the young generation is known as a copying collection, or I tend to call it an evacuation collection. In other words, I'm always going to evacuate young into a space that is empty, whereas tenured, I have to find I have to find the dead data and return that data to the free list. So this is a far more expensive collection, a lot more expensive to do that, right? So all the data is in tenured, but at the end of this, we might have to do something, especially for like a highly fragmented free list. We'll look at it and say, okay, yeah, because you could get allocation failures not because tenured is full, it's because it's too fragmented. You can't find a space big enough to support your allocation, and so in that case, you need to do a compaction, right? Which is then very expensive. Okay, so that covers sort of like the garbage collection. So cycle and how data moves around and everything. The question is how are young and tenured managed after startup? So these are like the runtime ergonomics, right? That we need to talk about, right? So how's the so at the end of the collection, we're going to resize things based on metrics that we've collected from the previous collections. We're going to use a lot of this tends to be driven by allocation rates. Unfortunately, we'll look at a chart and say that allocation rate is probably a kind of well, I published a chart on the Dev GC mailing list that basically said that it laid out all of the states. And one of the parameters of the states was allocation rate. And it turned out having allocation rate never changed the decision that was made as to how to resize. But that is the primary metric that's being used to drive when and how to resize. So yeah, so sometimes you get into these strange pathologies simply because things don't work. And I had some GC logs you can look at where you can see it and say, yeah, that wasn't the right response to what was going on. But that's understandable when you get there. Okay, so the runtime for ergonomics for the serial collector are a bit different in the sense that young size is based on the number of non-daemon threads running. So what they'll do is they will increase the heap by what this parameter here is, like the new size thread increase multiplied by the thread count, right? And they'll decrease the heap also based on that particular value. So that's on the assumption that each thread for that size of heap is going to generate so much, is going to consume so much memory before we have to call for a collection. And anyways, you get the idea is that they're saying thread can only be so busy, which is actually not as crazy as it sounds. There is limits on how fast you can allocate objects in memory. There's what I call a time to first byte problem that we have to deal with. Okay. So there's a bit of a code, so you can see it. You know, we pulled it out and just showed it just to show you that I can actually read C++ code. Okay. Tenure size is based on these things called min heap free ratio, max heap free ratio. Now, the funny thing is that this affects the size of the entire heap, not just tenured, which is kind of like a weird thing to do because, yeah, you'll see later when we get into a tuning strategy here. I need to get going here faster. Okay, so let's hand tune memory. And by hand tuning memory, you're going to see that we're going to try to follow the same strategy when we actually get into automating this whole thing. Okay, so what are heap tuning goals? We want to minimize GC interference. So that means we want to minimize pause frequency and we want to minimize pause durations. We also want to minimize memory footprint, right? And you're thinking like, wait a second, if I try to minimize all these things, like, they're sort of like, on different ends of a rope, it's a tug of war, right? And yeah, it's a tug of war. So, you're going to have to give up some place, somewhere, something. And also with the new requirements here, we have multiple, maybe homogeneous deployments or containers that are on a single server, and we want these guys to cooperate also, right? Right now, the cooperation is each one gets a quarter RAM if we don't set anything, right? But that's a quarter of the container's RAM, not the machine's RAM. But in this case here, we want to do something different and say, okay, we have RAM. You guys try to use it and figure it out on your own, like who gets what. And that, that's the part of the automated heap sizing here. So let's take a look at the different actors and roles, because this is going to help us with the strategy, right? So allocators facilitate cooperation between application threads and the garbage collectors. So that's, what we're going to say the role of allocators in this whole thing. Eden is a nursery. So that's a working space. So that's going to contain a mix of very short-lived objects. We call them transients, and long-lived objects, right? But generally, we're going to be dominated by transients. I would say that in most cases, transients are going to make up about 90% or even greater of the space of Eden by the time you go to collect it, which is really good, right? Because that makes the collection very cheap, because the cost of the collection, as you'll see, is based on the number of live objects in there after the collection. So if you only have transients there, then cost of collecting that space is zero. Right. Now, Survivor, we're going to retain medium and some long-term objects, because this is a space to give these things time to fall out of scope, so that we can collect them in a young generation collector where, the cost of collecting a dead object is zero, right? Which is not the same in tenure, where the cost of collecting a dead object is free space, freeless space manipulation. Free space list manipulation. Let's see if I can say that 5 times fast. Okay. So we have Eden, Survivor, and tenured. We only want long-lived objects in there, right? And so you can see that each of these spaces has a different role, which means that we can apply a different tuning strategy for each of them in order to get optimal performance out of each space and not have one space pollute the other space, and so on and so forth, right? Okay, so yeah, so when we look at a cost model here, the cost for young collection is going to be either dominated by scan for roots or copy costs of live objects, right? Because we're only tracing live objects, we're only finding live objects, and we already said that probably no less than 90% of the objects are dead, so they're not going to be touched at all. No, they're not even going to be considered by the garbage collector. Okay, but we do have to copy live out, so that's a cost. And we have to do the scan for roots to start the collection, and that can sometimes be costly. Well, the scan for root times is actually going to be generally a function of the number of threads you have or the size of tenured. Yeah, so for the full collections, which are in-place collections, you can see very expensive. Generally, they're going to be about 10 times the cost of a young generational collection in terms of latency costs. And again, it's going to be a function of the size of the heap and again, the amount of fragmentation that you have in heap, right? And we can actually do things. So the thing with fragmentation, we can actually do it. Like if you don't mix transients and long-lived objects, you're not going to get fragmentation, or not as much fragmentation. So you can see one of the strategies we want is to really make sure that we are tuning young generational spaces so that we don't actually start polluting tenured space with transients. And that helps with the fragmentation and helps with the frequency of the full collection cycles and the duration of the full collection cycles, right? And because we're doing that, we can actually, this is a strange thing, right? We're reducing latency, we're reducing frequency, and we can also reduce size. So it doesn't seem like that should be possible, but these are things you can actually achieve when you start looking after, the transient problem. Okay, so yeah, tuning strategy here. Young collections are relatively cheap. Aim for reasonable GC frequency, right? Now we could look at the young weak generational hypothesis. It's a curve, so if you got a curve, you can do some math with it and have fun with it. But one of the consequences of the weak generational hypothesis is that in a stable heap, where the heap size is neither growing or shrinking, pause times for a copying collector should be constant, right? And in these cases, they're cheap. So it doesn't matter how big young is, it's not going to affect the cost of the collection. What's going to affect the cost of the collection is how many live objects are in that space. Okay. Now you might argue that, well, if it's larger, I might have more volume of live, but which will affect the cost, and that might be true. But anyways, full collections are expensive. Aim for infrequent collection. Again, I said overhead, enlarge. So we want to enlarge Eden and Survivor to keep the transients from out of tenured space, and that's really the whole takeaway from this whole thing. I could have shortened this entire presentation by just saying that, right? And generally, we want the tenure size to be like 1.5 to 2x live set size once you've solved the transient problem. So now you can see what we're going to do is we're going to size each space individually and then push them all together, and that's going to be our max heap size, right? Or our heap size in general. Okay. So with the tuning strategy, we can get on to more of the questions. This is more implementation oriented. So I'm going to swap over to my cohort here, Saint, and he's going to talk about the actual some of the nuts and bolts of the C++ work, or some of what we're doing for the adaptive heap sizing. I'll stop rambling, Saint. Please come off mute and do take over if you'd like. Oops. No, actually, Mary, do you mind leaving my slide deck up? I'll flip through it for Saint. You can just tell me when he wants me to flip.
Right, sorry about that. I'm having a few audio issues here, but I think I should be good to go now.
Okay.
Yeah, so I'll just pick up from here with a question about how large should your Java heap be. So one of the questions that came up earlier was about who is responsible for deploying the app and tuning it. And one of the things that people often look at when they are trying to figure that out is using the XMX flags to set the size of the heap. But once we start thinking about how big the heap can be, we realize that there are some complications. So the amount of physical RAM you have or your container will obviously limit how much you can use for the heap. But one of the problems is that the JVM is using native memory, which is separate from the heap. So it's hard to reason about overall heap size when you don't really know what all these native components are. So on this slide, one of the things that we see here is that we have the Java heap in the center here, which is green, but there are a whole bunch of different other things that are happening on the system. So in the same process, for example, there's a class space, code caches, IO buffers. And so just reasoning about how big the heap should be becomes very complicated. There are also the OS data structures, like the text and the data. And these are typically shared across processes. So should they count just once? Should they count multiple times? So how much memory do you really have available for the Java heap? That can be a tough question to answer. Now, this is kind of where the idea of tuning comes in. And there are different collectors like ZGC and G1GC that are already looking at this problem. And with Google, for example, there's a talk presented by Jonathan that essentially shows that they saw a drop in container OOMs once they started experimenting with automatically tuning the size of the heap. So there are different challenges that using an automatic tuning strategy can resolve. So one of the things that we see is that the behavior of a garbage collector is extremely hard to predict. So essentially, it ends up just appearing like a set of random events. And this can be the case even if you have identical configurations in in different deployments. So it becomes hard to know what is the optimal configuration that you should use, because now you have to have a deep knowledge of how GC works. And then adding on the complexity of containers kind of makes things even crazier. So the idea is, instead of just kind of using, like the startup ergonomics and those kinds of things, changing XMX, those are all guesses, and it's better to measure what the application is doing and then adjust accordingly. And that's the idea behind automatic heap sizing. Typically, max heap size will be, in such a strategy, you want your max heap size to not restrict what the JVM can use. And so the idea behind automatic heap sizing is to reserve all the memory that's available, but you're not committing all that memory. Because if you commit all that memory, then you're likely to run into the OOM killer events. And so what we'll look at here, I know we are kind of running short on time, is we'll look at how we want to resize spaces, both young and tenured spaces, in order to achieve this automatic heap sizing. I'll just skip ahead and talk about this concept of GC overhead that Kirk introduced. So we talked about how there is just one collector thread and there's a bunch of application threads that are running. And then when a collection happens, the collector thread takes over and all the mutator threads stop. And so that amount of time that is spent by the single collector thread as a fraction of the overall time in the application is what we're calling GC overhead, as we mentioned earlier. So when you are automatically tuning the heap size, we are going to use GC overhead and memory pressure to figure out what to do. So for example, if the overhead is high, this first row here, then what we want to do is to increase the size of the heap. Memory pressure is low, which means that this is an option that is safe for us to do. And what that will do is, by having a bigger heap, that means we are likely to have the mutator threads run longer before a garbage collection is necessary. The case on the other end here is, what do you do when you're below the GC overhead threshold? And the threshold is something that I can show here real quick. It's just, we are treating that as a parameter that you can specify to the JVM. So perhaps you're looking at the events, the garbage collection events over the past 15 minutes, say, and that's an option you can set in the JVM. And so if you are below that threshold, then it means your garbage collection thread is running less than you want it to. And so the action that you should take in that case is to reduce the size of the heap. There's a concept of tuning also, which essentially determines what is the rate at which objects are promoted from the young generation to the tenured generation, because there are problems that need to be avoided, like premature promotion. And so with this idea of resizing the heap to meet the target, or the overhead target you have set, there are some challenges. In the current implementation of the serial collector, the ratio between the size of the young generation and the tenured generation is determined by a ratio. So once you know the heap size, a ratio is used to split the young and the old generations. But this ratio is fixed at startup, which means that later on when the application is running and these sizes need to change, that becomes a challenge. Another challenge that we run into is that essentially all of the data that we are interested in moving around in the heap, if you remember the chart that Kirk showed where the data is in the young generation and then it gets promoted to the tenured generation, one of the things that you'll observe is that all of the data ends up in the tenured generation after a full collection. Why is that a problem? Let's take a look at this. If you have your data in the tenured generation, sorry, this is just after we've resized. Yeah, I'll go ahead and use this slide. So why are we swapping the young and old generations? So after a full collection, remember we say that all the data is in the tenured generation. In the current implementation where the tenured generation comes after the young generation, then we would have data higher up in the address space. But what is shown here is actually what we want. We want after a full collection to have all the data in the tenured generation. And what this enables us to do is to say, okay, if we need to shrink the heap, it's easy for us to do because all the data is at the bottom end of the address space. And in the current implementation of the serial collector, these are two separate reserved spaces. So then what we want to do to assist automated heap sizing is to actually just use one whole reserve space so that all of the tenured and young generation data are all in just one reserve space. And then once that space is committed, it's easy to uncommit from the end of that space to return memory to the operating system if we are shrinking the heap. So that is something that that we would be able to do now. So I'm just going to show a quick demo right here just to give us a feel for what this looks like. There is a sample application that I wrote, and there's a Docker file that I've created that launches JDK21.
Just a second here. I think, Mary, do you mind switching to Saint's screen share?
Okay, yeah, sorry.
It's okay.
Am I sharing the screen now? Is that visible?
Yes, it's good.
Okay, so there's a simple application here, and there's a lot of arguments here, but the only thing that I'm highlighting here is that we're using JDK21. I'm explicitly selecting the serial collector, but we will not need to do that if we run the container with the appropriate parameters. All right, and then I'm going to do a Docker run. I'm going to say 2 CPUs and 2 gigs of memory and run this sample application with JDK21. So we're not that concerned with what the application is doing. We're just interested in the fact that we've allocated 2 gigabytes to the container and 2 CPUs. And then if we run Docker stats, we can take a look at the memory usage in that container. So the default ergonomics of the serial collector have ended up giving us about a 32 megabyte heap that this application is using, even though the container has 2 gigabytes available to it. Now, just the fact that that's 32 megabytes doesn't mean that that's a bad thing, but that might not be what the application actually needs. This is just what we're getting by default. Now, I will I'll launch a different container here. And this is going to use a build that I've been working on, a prototype. And what it's doing is using this concept of GC overhead and figuring out, okay, we have a target GC overhead of 5%. So let's change the size of the heap to keep us at that GC overhead target. And now if we look at the Docker stats for this particular application, we can see that it has settled in at about 1 gigabyte of usage in this container. And the interesting thing to observe here, the key thing to observe is that of the parameters that were given to the JVM at startup, there is no XMX argument telling the JVM how big the heap should be, what the max size of the heap is. And so in this case, the heap size is automatically changing. It's adapting to the environment that it's in and the GC overhead that it's encountering.
Yeah, and it's already bigger than the 25% limit.
Yes, and this is already bigger than the 25%
That limit,
default
yeah,
heap size
cool.
that is selected. So I just wanted to show real quick what that looks like in a container environment, the difference between the default implementation and what you can do with automated heap sizing. So we have a bunch of next steps here. ZGC, for example, has been working on a similar concept. And in the ZGC implementation, there's a concept of global memory pressure where you figure out how much memory is available in the environment. And that is something that changes dynamically. And so you don't want to just pick a heap size and stick with that because your environment is dynamic. So if the amount of available memory decreases drastically in the environment, then the JVM needs to be able to adjust and say, actually, I don't need that much heap right now. A lot of it is free. I'm going to uncommit memory and be a good citizen on the host, and therefore, make memory available for other users. And then, of course, we're changing the ergonomics from this min-max heap-free ratio to GC overhead. But then the resizing algorithm used by this GC overhead calculation in automated heap sizing is probably something that should match what ZGC has because they have some resizing logic already implemented. So what we have here is just, it's a logic in our prototype, but we have not synchronized across what the other collectors are doing. So that's part of the remaining work. And right now, this resizing is happening only on a full collection. And so we need to look at what can be done for just young collections as well. And then, of course, with this type of change, lots of testing and benchmarking is required. And so one of the tests that we are running is hyperalloc, which stresses the garbage collector, and then seeing what kind of behaviors there are, and how does the heap size evolve. So that's just a high-level overview of the direction that this is going. So thanks. I'll hand it back to you, Kirk.
I need to unmute. Okay. Yeah. Okay. So that's a pretty cool piece of work. It was like just the initial steps that we had. Actually, I don't think it was working until very recently. We were getting all kinds of zigzag V's and stuff like that because a lot of the work of switching the spaces around so that they're upside down. It's like some of the calculation for determining if an object is in young gen is if its address is less than the base address for the tenured space. So obviously those type of calculations are going to fail when you start doing this rearrangement. But it was really kind of necessary to get the data out of the way so we didn't have to copy it when we wanted to resize. Okay, so finally, I just want to say that a lot of this work has been driven by making the JVM more container aware, container friendly. And so there's this paradox, right, that exists actually here. Is kind of weird, right? Because having Java Heap use 25% of a container's available memory actually ends up saving you memory overall in the system, right? One of the suggestions that we've dealt with is like, well, let's just set the percentage up, or you can use max RAM %, which is a setting that I don't recommend that one use. But anyways, let's just set that value up to 70%. And that actually ends up wasting memory, because if you don't need to use that much memory, then what happens is that you're going to end up using it anyways, right? Whether you need it or not. And so that's one of the reasons why we wanted to go to adaptive size, this automated size, because we just wanted to use real data to say, okay, what size does this actually need to be, right? Anyways, so the other thing too, I think, is that when we get into these large deployments, you just get some harmonics in the systems that are really weird, and so you could take a sample out and say, oh, this looks like a good configure for this JVM, but all of a sudden you figure out like, oh, it's not, right? Because maybe I picked the wrong one, or what we have is for a large deployment, maybe there's like 8 or 10 different optimal configurations, but they're only optimal for individuals, right? And not optimal for anyone else. And so the question is, how do you figure that out? You can't. So by automating this, then you can just have the system figure it out on its own, right? And hopefully this also leads to better cooperation, for instance, between memory. Like I know with the testing with ZGC, they found that they just weren't getting killer events when they should be, just because everything settled out, and some balance between everybody had enough memory to work. Maybe not overall, they probably could have used more, but they had enough that they weren't actually being killed. If you don't give the system enough memory, in this case, you're going to get what you get, right? So if you need 2 gigs and you're only giving it 1, so be it. And which leads to the last point here, which is like the best way to tune is to know what is needed and ask for it. Generally, with garbage collection, we don't tend to fine tune right down to last byte. What we tend to do is tune into bands, right? And so if you know approximately which range that you need to be in and ask for that, then you're going to tend to get better results than just trying to guess at what. I think what we see is a lot of deployments, like a lot of the serial collection deployments, are people just deployed the application that way because they just, ops was given it to deploy. They didn't know, so they just deploy. And at that point, like you said, you get what you get. And if performance is important or tail latencies are important, then you really need to dig down a little bit to try to figure out, just what are the sources that you actually need, and to make sure that you're appropriately resourced. And I think that's about all we have to say, and we're 3 minutes over, so we should stop, and we can go for questions if there's anyone here that wants to ask anything about GC, this implementation, plans for next conferences, whatever's happening here. We'll let you in please post your questions for Kirk and Saint if you have any. And we're sitting here anxiously waiting for questions. You're muted, Mary.
Okay, thank you. Yeah, I always mute my phone.
You always mute yourself. So do I too. Yeah.
Yeah. Thank you for reminding. Yeah. Yeah. I don't see any questions right now. Yeah. No. Everybody's quiet.
Yeah. So we either bored them away or blew them away.
That's right. Yeah.
I don't know which one, but
exactly. And everybody has your contact information, right?
Yeah, I put my
so
Twitter. Well,
we know
that's
how
my social needle. And how are the new versions of Edge going to affect this?
Heinz.
Gen Z? That's a really good question, Heinz. So I think in JDK 24, 25. Well, I'm not sure where the work is yet. I don't know if it's 24. Do you know where it is, Saint?
No, I don't know where that is, where that stands.
Yeah, so it's actually being released in 24, and they actually are going to use the softmax heap size, and they have another parameter there that we don't need to try to give the system hints as to how to resize. But effectively, it's going to work approximately the same way of how it's working in the serial collector. In other words, we want to be able to give memory back to the system whenever we can to help with overall memory pressure on the box. And we want to just make sure that applications have enough memory, and we want to minimize the amount of tuning that people have to do. I mean, that's always been a goal. And I think this time we have a real shot at it. ZGC was actually put in by Eric Oosterland and some of the other guys at Oracle. So I think Google, Microsoft, and Oracle were all independently working in the same direction. And then all of a sudden, I think at JCrete last year, we came together to help sort this out. What do you think about the always pre-touch flag? Should that be used in general? Always pre-touch. I don't know. I honestly don't know the answer to that. You probably have the answer in your head, and you're just trying to fish an answer out of me right now. It's my guess. Knowing you, Heinz, I don't know. I mean, the always pre-touch means that you're always going to be committing the page before you use it. So that's, as opposed to if you don't pre-touch it, it's on first touch is when you're actually going to have it committed. So it's a what do we do? Do we do it lazily or do we do it proactively? I think, and there's costs and benefits in both directions, and I don't know. I think you'd have to A/B test that with your application to know what's the best thing to do, and even with A/B testing, you'd have to be careful about how you do that. But great question. You've stumped me. We call it stump the chump. There we go.
Awesome.
That's a good question.
Yep.
You have an answer, Heinz? See if he puts it in the comment.
That's right. I'm watching.
I'm watching for his comment because his comment will be better than my answer.
Oh, question. Yes.
There's always been a lot of disagreements about XMX says, what is your latest best practice? No, you don't. Okay, that's the first. Best practice. I have never been a fan of setting XMX to XMS. That's your initial size. I think people used to do that. So tradition started, I think, with CMS when resizing was not as efficient as it is today. But it actually turns off, it affects adaptive sizing and the ability to resize the heap. And our goal is to get rid of having to set XMX, period, and having the JVM do something reasonable. And only when we've messed up, will you be forced to actually even set any of these flags? So hopefully it works. I don't know. My fear is, and this one, if I can state my fear, is that once you get into all kinds of deployments, there's all sorts of harmonics in these systems that cause weird effects, and you start seeing things that you don't expect to see. I know we did a large AI study on as many GC logs as we could get our hand. Well, I wouldn't say as many GC logs as it was practical to analyze, to try to see if we could find clusters that we could use for pre-tuned JVMs. And I'd say the randomness in the system just completely destroyed that effort. Now, I think we were going about it incorrectly. So if we're to do the same exercise again today, I think we possibly could be a little bit more successful at it. But, there's a lot of randomness in garbage collection, and that's just a reflection of some of the randomness in the system. And it could be just as simple as to how your JVM gets laid out in memory. If you have a good alignment across pages, then things will work out well. But if you get a poor alignment, then all of a sudden your performance can get hit like hundreds of orders 200, 300, 400%, like that.
Another question.
Have an adaptive sizing of XMX. Would it perhaps? I think we do have an adaptive sizing of XMX right now. I mean, I'm trying to guess at what you're saying here. I understand it saying like, if somebody sets a bad XMX, then just ignore it, maybe, and just use more if there's there, or use less. Well, you can always use less, right? The problem with that is more. But that's what we're trying to do. Is just, like, since people have so much trouble trying to decide, it's like, well, why not just let the runtime decide? So if we set XMX to the amount of resources available, be it limited by container or the machine, because what I didn't show you in that code is actually it looks at the container limits, but then it looks at the machine limits. And if the machine limits are less than the container limits, then the machine limits win, right? So at that point, that's why we put in like yet another flag, which is the soft max heap size, which is the XMX that we actually can't ignore.
Okay. No.
I want to
Another.
get away from having said, yeah, that's exactly what we want to do. Yeah, and yeah, I would say always pre-touch is probably something that you don't want to do. But I think people will discover that hopefully when they start using it in the wild. We don't want to pre-touch because pre-touch means we're going to commit. And we don't want to commit until you have to. Awesome. I don't know if Vincent is still around or did he disappear to the next, go watch Holly or whatever.
Right. So. Yeah. I don't see any more questions. And yeah, maybe Vincent's at the other session. So yeah.
Well, that's an awesome comment, Heinz. So.
Yeah, it's a great presentation. Yeah, and I think folks can always reach out to you, to Kirk and Saint, if they have more questions. So, yeah.
Yeah, absolutely. Yeah. We're always available for questions. Actually,
that's right.
No one's been asking us any questions for a long time, so
that's right. Yeah,
we're feeling lonely. We'd like some questions.
Yes. Yeah. Shoot more questions.
More questions. Yeah. Right. Okay.
Should
we?
Yeah, we
call
can.
It a night?
Yep. Let's do that.
Okay.
And yeah. So. Thank you so much again. And I'm going to end the stream. And thank you again for joining this session. But Kirk and Saint, please stay on. I'm just going to end the stream. So thank you and goodbye.
Okay. Cheers.
Thanks.
Thanks. Thank you. And these actually not a bad question. I just got